Let's discuss the following problem. We discussed the idea of a solar cell. Let's take it one step further. So the U.S. military laser weapons in megawatt range. Suppose I take it a bit further and have a 100 megawatt laser. Also, the laser is perfectly collimated, so it does not spread over distance. I want to launch a perfect reflective iPhone, the mass is about 100 grams or so, to Alpha Centauri, which is about 4 light years away, by 4 times 10 to 16 meters. If I shine the laser on the iPhone for about 1 month, how long would it take ISO to start ignoring acceleration phase? Uh, um, uh, how about if I shine for 1 year, right? So let's go ahead and figure this out. Well, what might be unrealistic iPhones or semi-small spacecraft about Alpha Centauri? So I'll answer basically first A and B, and then you guys can think about what how to answer C. All right. So I do have a 100 megawatt laser. So luminosity of my laser is 100 megawatts, right? And I made it perfectly collimated, so it goes straight as a perfectly beam, right? So now I'm gonna hit my iPhone. So here's my laser. There's my spacecraft or my iPhone, and it's going to reflect light back, okay? So the force I'm going to exert on this thing is going to be the integral of the flux times the area divided by C, right? Well, flux, I'll write like this. And so essentially, flux times the area, because it's perfectly collimated, that means all the luminosity will hit this thing. This is actually really just L over C, okay? So let's go ahead and figure that out. So this is going to be 100 megawatts. So it's 100 megawatts. So it's 100 times 10 to the 6. So this is 10 to the 8 divided by C, which is 3 times 10 to the 6. 6 times 10 is 5. Sorry, 5 meters per time. Sorry, times 10 to the 8 meters per second. All right. Okay, so let's go ahead and do that. So this is just going to be surprisingly a very, very small amount of force, it turns out. So this turns out to be something like 10 to the 8 over 3 times 10 to the 8. That's basically about 0.3. I even make it a little better, 0.33, whatever. 0.3 is fine for the purpose that way. This is a force. This is equal to mass times acceleration, which is equal to 0.1 kilograms times A. So it turns out A is not that small. A is about 3 meters per second squared. Okay, that's pretty substantial, right? So now I want to ask myself, how long if I shine it for about 1 month? Okay, so a month is about 30 days times 24 hours times 360 seconds per hour. All right, so let's go ahead and compute that out. I don't have a calculator on me, so I just got to do it on something else. So let's see, those 30 days times 24 hours times 3600. All right, 1e6, make sure that's right. Okay, so this is about basically 2.6 times 10 to the 6 seconds. All right, okay, so basically the velocity then is just going to be a times t, right, which is 3 times 2.6 times 10 to the 6. So that's simply going to be, if I compute this thing correctly, that is a 7, I believe that's 7.8 times 10 to the 6 meters per second. All right. Okay. So how long will it take Alpha Centauri? So Alpha Centauri is, the distance is, I wrote up there, is 4.4 times 10 to the 16 meters. So that's so the time is going to be distance over velocity is 4 times 10 to the 16 divided by 7.8 times 10 to the 6. This is roughly 8 or so. So it's basically 0.5 times 10 to the 10, which is 5 times 10 to the 9 seconds. All right. Now 1 year is equal to 3.15 times 10 to the 7 seconds. This is something you just know, right? And so this is actually equal to, if we compute out what that looks like, I wrote 5e9 divided by 3.15 e7. That's about 150 160 years. 160 years. Okay, that took a while, right? So now let's imagine if I shine it for a year. So for part B, that's not too hard, right? I already compute what my velocity was earlier, okay? So I could just basically velocity of 1 month times 12 months, right? So that's just basically 12 times 7.8 times 10 to the 6, all right? And we do that, it's basically 7.8 times 12, right? That's 9 times 10 to the 7 meters per second, right? And now the time, again, is just going to be 4 times 10 to the 16 over 9 times 10 to the 7. Well, that's going to be, this is roughly, again, about half or so. 0.5 times 10 to the 9. Five times 10 to the 8 seconds, right? So that's about a tenth of that, which is about right, okay? So it can be a little smaller, right? Because they made an approximation. So about 16 years here, right? Okay, and I'll let you figure out why this is impractical in part C.